For the beginning of this lesson, we are going to introduce you to the inverse of an exponential function. The inverse of an exponential function is actually called a logarithm. An exponential function is a one-to-one function. As you can see here in the first statement, we would just switch the x and the y to create the inverse. Now, to get back to that y being by itself, to write it as a function of x is a little bit tricky in doing so, but we'll just go ahead and show you in this concept box what a logarithm looks like. Now, one of the commonalities between an exponential function and a logarithm is their base. So if you ever see a base in the exponential function, which is represented by the b in the function, the logarithm also has a base that is the exact same as the one in the exponential function. And so this is a quick little easy link between these two functions. Now, the very first thing that you're going to have to learn how to do is rewrite logs to exponential form and exponentials to logs. What I like to do is just show you a little trick that I tend to do to kind of give myself some guidance. And I'll look at example number 1 just to kind of show you. So if I have something written in log form, and I'll just take this first one. This is log base 2, so you can see the 2, 32 equals to 5. Now, I know that my exponent form, the base of the log and the base of the exponential form have to be the same. So I know that I'm going to start with 2 as my base. And so what I'm going to do, and I just use this little circular trick, I'm going to say 2 raised to the 2nd power, 2 raised to the 5th power is going to equal to 32. And so that's going to be a base of 2 raised to the 5th power is equal to 32. And you can see that that is the exponential form of the given logarithm, and so that tends to work well both ways. And so I can show you another way is also. So if I take part B, I'm just going to say 5 to the 0 power equals 1. I know that when I write the logarithm, the base has to be the same as the base of the exponential, and so that's going to be a log base 5. And again, I'm going to use this little circular part. Base 5 of 1 is going to equal to the 0. And that would be working back from exponential form back to logarithmic form. And so that circular trick kind of works both ways with converting from log to exponential. So it's very important that you get comfortable doing this very early on with logs and exponents before we start diving down into the actual inverse relationship. So if you take a look, there's a couple relationships here in this concept box that are very important, and I think the second one is truly important. Log base b of b equals to 1, and that is going to be an important property of logs that you're going to need to know for later lessons, especially when we get into solving logarithmic equations. So it's something you definitely want to know. So go ahead and take a look. You can look here on your calculator. If I go to the calculator part, log is a second function button, and it gives us a little part for the base and then a bigger part in parentheses, and you can use your tab button or your arrow to work between those two parts of the calculator. So if you go ahead and just take a look at sample problem number 1, sample problem number 2, and sample problem number 3, and just give those a try and come back and look at the solutions. Okay, so the very first sample problem just asks us to evaluate the expression in our calculator, and that's as simple as just taking our calculator, hitting the log button, and then putting in the base that's required. So I'm going to hit 4, and then I'm going to tab over to the next part, and then I'm going to put 64. And if I hit enter, and that'll be 3. So we know that this evaluates to 3. Another way that you could look at this, if you wanted to make it an equation, you could say, what would x equal if you had log base 4, 64? And you could say 4 to the x power is going to equal to 64. So 4 to the x power equals to 64. Now, you probably won't know the exponential part of these forms for every one of them, but since you have worked with third powers and second powers and fourth powers, some of these might look familiar to you. So 4 to the third power equals 64, and so we know that 3 is the correct answer. For part B, log base 32 of 2 actually equals to 0.2, which is probably what you got in your calculator, In many cases, you'll see it written as 1/5. So just double check when you're doing Math Excel to please watch the blue directions and see what they're asking for. Sometimes you'll give a correct answer in decimal form, but they'll want the answer in fractional form. So you definitely want to be careful of that. All right, let's take a look at sample problem number 2. So here we're just writing back and forth between the two forms. So we're going to go from exponential to logs. So the first thing that I like to do when I do this is just simply write my log and then my base. And my base is going to be the same as what the base was in the exponential. So I know those bases are going to be the same. Now I'm going to go to 100, and that's going to equal the 2. And you can always test this. You can put log base 10 of 100 to see if it comes out to be 2, just as well as you could test 10 squared equals 100. Alright, so let's do part B. So we're going to be log base 3 of 81 is going to equal to 4. Okay, and sample problem 3 has us working back the other way. So I'm going to use the same base. Base 3 raised to the second power should equal to 9. So it's base 3 raised to the second power equals to 9. And then same thing over here. 8 to the 0 power equals to 1. Alright, so let's go down to the next part. Now, notice up here in sample problem number 2, part A, we had log base 10. Log base 10 is what we call our common logarithm. And what happens a lot of times is that if it's log base 10, you don't tend to write the base 10. You can write it without it. So you can see here log base 10x equals log x. And so you'll just want to become familiar with that. Okay, so let's do sample problem number 4, part A in our calculator, log base 5. So if I put here log, it gives me a place for my base, but I'm just going to leave it empty. I'm going to put a decimal place so I can get a decimal. So log 5 is going to give me 0.69897. You could put all that in your calculator. That's not the full decimal. If you wanted the full decimal, you could simply multiply by 1, and you can see the full decimal right there. Another way for you to do that is if you could go back up and highlight it and hit enter, you can see the full decimal there as well. Now let me bring your attention back up to our original log. Do you remember we skipped the base? We didn't even put a 10 in there, but after we hit the calculation, it automatically put the base 10 for us because it was understood by the calculator. So just a handful of calculator tricks there for you. Alright, so log 5 is approximately 0.69897, and then for 7, log 7, that's approximately 0.84509. Alright, that's a good start on logs. Now we'll take a look at logarithms in a functional form. So we know that if we have an exponential function, we have the inverse is a logarithmic function. And if you recall, an inverse of a function is reflected across the diagonal y equals to x. And so you can see here in this particular graphic that we've given you, the red and the blue graph. And the blue graph is the logarithmic function. So I've also done another one on the calculator here. So we have 2 to the x, and then we have log base 2 to the x, and so you can see they both have the exact same base there. And then I went ahead and did y equals to x so you could see the diagonal. Now, a couple things to note. If we had the exponential function and the x-axis was the horizontal asymptote, as we take the inverse, the logarithm, the y-axis actually becomes a vertical asymptote. And then the same thing with the intercepts. If we see in the exponential function that the intercept was 0, 1, then now we're going to have an x-intercept of 1, 0. So you can see that based off of the calculator, we basically reverse or flip everything around as far as domain and range is concerned, intercepts, asymptotes, and things of that nature. So it's very important that you get a feel for how to sketch logarithmic functions. Now, just as we had with every other function, the base function is logarithm. Log base b of x is the parent function, and then of course we can put in our h's and our k's and an a value as well, and they have all the same properties that we had with other functions, with the stretching and compressing and the translations as well. So what I'd like you to go ahead and do is to just make an effort at sketching, following examples as best you can. If you need to t-chart a couple points, that's fine as well. Okay, if I look at sample problem number 5 here, if we're t-charting, for example, if I were going to do this with a basic t-chart, if you recall back that log base 3 of 1 was going to equal to 0 and log base 3 of 3 was going to equal to 1. These were two properties at the beginning of the notes in a concept box that I said were very important. And so you can see here that's a really quick way for us to get a couple points. So if x is 1 in this case, then y equals to 0, and if x is 3, then y equals to 1, and we know that the y-axis is going to act as a vertical asymptote, and that would be a quick sketch of that given logarithmic function. Now, in the one down below, we have some transformations going on, so the simplest thing to do may be to graph log base 4 of x before you even get started. And if you did that, simple t-chart again give us 1, 0 and 4, 1. Those are always really simple points that you can work with, and so your parent function is going to kind of look like that. Now we know that this 3 right there is going to move us 3 to the right, and that 4 right there is going to move us up 4, because that's our h and our k. So if I went 1, 2, 3 to the right, 1, 2, 3, 4, I could move each point. And then also, with the fact that we're moving 3 to the right, we also have to move this vertical asymptote 3 to the right, and so we have a new vertical asymptote there. And so we would just simply sketch the same way we did the other one as best we could. That gives us a general sense of how to sketch logarithmic functions.